Okay, so what did we talk about last time? So last time we did bunch of stuff about basically a bunch of stuff about constrained optimization, right? So we talked about KKT conditions. We talked about line searches the last time a little bit, right? And like, you know, inequality constraints, that type of stuff, right? So we're gonna pretty much continue in that vein today. So what we're gonna do today, we're gonna kind of go back to some of the algorithms for handling inequalities that we started talking about last time. In particular, today we're gonna talk about kind of my lab's sort of like workhorse algorithm class for solving these kind of problems. This is called the Augmented Lagrangian method. Then we're going to look at a particular class of constrained optimization problem that is basically the bread and butter of modern model predictive control. So super applicable all over robotics and aerospace problems, this kind of stuff, called a quadratic program. So who's heard of a quadratic program in here? Like a good number of you, right? So this is stuff. So today we're going to show you how to make a solver for a QP, which is cool. And that's on the homework. We're going to do that. We'll check one out today. Then we're going to talk a little bit about some more. So this is like kind of, today should be the last day about like kind of basic optimization algorithms. And then like next time we should really dig into optimal control. So there's a few like cleanup details on sort of numerical optimization tips and tricks kind of stuff. So we're going to talk a little bit more about line searches and regularization, but some details on how to apply those methods to the inequality constrained case, basically. So I'll say like more on regularization. Okay, cool. So let's dig in. So first, I just wanted to like kind of recap what we left off with last time. We talked about KKT conditions for inequalities, and then we talked a little bit about different methods for solving those problems. And so we kind of left it off with the penalty method. We're going to pick up there again because that sort of directly leads into the augmented Lagrangian idea. So the basic idea we said last time is to replace inequalities with an objective term that penalizes violations. In particular, last time we talked about a quadratic penalty. You can really make up other penalties, right? You can have any kind of penalty you want, but the quadratic penalty method is kind of the standard one. And so here we go. So we gotta do this. We go from min f of x subject to say c of x greater than or equal to 0. We take this and we turn it into min over x f of x plus this penalty function. And we're gonna define it like this. There's other flavors of this that you can make up, but this is kind of a pretty standard one. So this min is in here to clip the constraint function, right? So we're only penalizing the violations, i.e. we're only penalizing negative values, right, that are violating the inequality constraint. And we just take those violations, we square them, multiply them by some tuning parameter rho, add them to the objective, and we minimize that function, right? Does that make sense, everybody? Did we talk about the fact that this is non-smooth last time? Does this seem weird to anybody for Newton's method? Does anyone think there might be a problem here doing Newton on this? Thoughts? Anyone have any thoughts? No thoughts? So it looks a little sketchy, right? This is not C2 smooth because of that. You know, it looks like we kind of drew this last time, right? So if I have sort of x, and then this penalty function, assuming that we're penalizing positive worth in here, just x greater than or equal to 0. This looks like this, right? So it looks like a one-sided quadratic parabola. Is that function smooth? Question. Anyone have any thoughts? Speak up. No? I heard somebody whispering. Yeah.
The derivative is 0 of like the quadratic at 0.
Yeah. So it's C1, right? The values match and the first derivatives match. So it's C1, which is good. It's only got to jump in the second derivative, right? So it turns out that's allowed with Newton's method, and Newton's method will still work on this, which is fun. So that's cool. So we talked about how basically this is easy to code up, right? Like this is really, really simple, but that it has some issues. Namely, it gets ill-conditioned. Does anyone know what I mean by ill-conditioned? Anyone done any numeric? Yeah.
It has to do with like the ratio of the eigenvalues, right? Like the largest eigenvalue to the smallest eigenvalue.
Yeah, exactly. So I'm adding this term to the Hessian, right? And that term, let's say that it's just x positive. Basically, any terms that have an active constraint in the Hessian of your that shows up in Newton's method, you're going to get if rho is really big, you're going to get eigenvalues that basically go like rho, and those are going to dominate and make the matrix sort of really kind of ugly and hard to invert. And as a result, you're going to get lots of floating point error and stuff like that. So big penalties in here cause problems is basically the problem. So what that tells you also is you need large penalties to get accurate constraint satisfaction. So that combined with this fact, ill conditioning as you get large penalties, tells you you can't really get accurate constraint satisfaction with a penalty method. As you crank up rho, you'll get tighter constraint satisfaction, but you reach a limit where you can't crank it up anymore and still solve the Newton linear system that shows up, the KKT system. In particular, if you look at the theory for these guys, to get perfect constraint satisfaction, exactly C of x equals 0 with this guy, turns out theoretically you actually have to crank that rho up to infinity. So obviously we can't do that in a computer with floating point math, right? So this is basically the story. These things have this issue where you basically just can't get past a certain constraint tolerance. So what we're going to do now is fix that issue with a trick called the Augmented Lagrangian. So basically the trick is we take the penalty method, which just has that quadratic penalty in it, and we add a Lagrange multiplier term to it, which we all know about now, right? And we're gonna, so let's see, I'll write this down, we'll talk about it. Okay, so what we're gonna end up doing is something like this. And I'm gonna write a little tilde on this lambda to indicate that it's not the exact Lagrange multiplier. Okay, and then this thing looks pretty much exactly like the Lagrangian we had before, plus the penalty term, right? So we call this whole thing now, we write it like this, L sub rho, which is kind of the penalty thing, x, and then lambda tilde here. This is called the Augmented Lagrangian.
Hey, Zach.
Yep.
Can you explain why the penalty constant is adding and not subtracting?
The idea is, well, so the thing in front there is squared, right? So it's always positive. And the penalty, the idea with the penalties, I want to make the objective worse, right? That's always the idea. So when I'm violating, the objective value should get higher, should get strictly worse. Does that make sense?
Yeah.
Yeah, so same with the Lagrange multiplier term, right? So if C of X is negative, that's bad, and lambda redefined to be positive, right? So that's why that term has a negative in front. It's so that when you're violating, that term's making the objective higher, making it worse, right? Does that make sense? Yeah.
So both X and lambda tilde are like optimization variants.
No, not right here, right? This is min over X only. So we're going to talk about that in a sec. So basically what you're doing here is that term's sort of part of the penalty. And we're going to do some outer loop tricks to update this lambda estimate. That's sort of what the augmented Lagrangian method is. So this is not a primal dual method where we're doing Newton over both X and lambda. That's sort of the main difference between what we talked about before. Yeah. Okay, so so we do this.
Scroll up to the first page.
Yeah.
So here, was that a f of x plus p rho over 2?
Yeah, that's a plus.
Okay, I thought that was a minus. That's why I was a bit
I
confused.
had to- yeah. So if you're maximizing, it would be a minus sign, right? That's the
Right.
whole idea, is supposed to make things worse for you. Okay, apologies for bad handwriting. Okay, so the idea is we do this, we solve this minimization problem, and then we update our lambda estimate, this lambda tilde, by sort of, you want to think about this as like offloading the penalty term into the Lagrange multiplier term. I'll show you exactly what I mean. Okay, so this is what this looks like. So when I write down the first order necessary conditions for this minimization problem, gradient equals 0, here's what I get. I get partial f partial x minus lambda tilde times partial c partial x plus the penalty looks like rho c of x transpose partial c partial x, right? And I'm ignoring the min sort of switchy guy in there for right now, assuming this constraint's active, okay? So this, I can rewrite this slightly as partial f, partial x, and then I can group these terms, the lambda and constraint term together to look like this. Okay, so the takeaway here is this rho times c is acting exactly like a Lagrange multiplier here. Does that everyone see that? They're basically doing the same thing. So what I do is I solve this problem with the penalty in there. Once I've solved it, I'm going to take the rho times c penalty term and stuff it into the lambda in this outer loop and update lambda. Now the next time I plug that new lambda tilde estimate in and then solve the first problem again. Right, and that's my iteration. Does that make sense, everybody? So this sort of says, what I want to do is lambda tilde gets lambda tilde minus rho c of x, roughly speaking. Does that make sense? So I push the penalty term into the Lagrange multiplier term. In parentheses for active constraints. So that's sort of the hand wavy. So here's the full detail version. So I want to do first min over just x, so just the primal variables, right, of this augmented Lagrangian. So lambda tilde is a constant as far as this step 1 is concerned, right? Only min over x. Then the next step is update the lambda estimate. That looks like this. So here's sort of the trick for active constraints specifically. So this is basically just clamping stuff to keep lambda non-negative, right? Does that make sense, everybody? So we want the Lagrange multipliers to always be positive in the inequality case, right? So that's making sure that happens. And then the last step is we crank the penalty weight. So usually we do something like rho gets alpha times rho. And this alpha is usually something like 10. So something like we crank the penalty up by a factor of 10 each time around the loop. There's lots of details in here. You can tune this a bunch of ways. You can skip the row update entirely sometimes. So there's a bunch of stuff in here. But the idea is, compared to the penalty method, with this one, the last step's actually optional. I can leave that row alone, and I can just do these lambda updates, and I will converge to the correct answer. I'll converge to the correct multiplier and the correct solution without necessarily having to crank that penalty up super high and get ill conditioned. So that's the trick. Is everyone good with this? Any questions? Yeah.
What do you start lambda at?
0 usually. Yeah. So in the first round of this is just the penalty method. And then as you go, you start updating this lambda with this outer loop, and you'll eventually converge to a good primal dual solution, both x and lambda. Cool. Yeah.
Does this require that your initial point is feasible?
No. I mean, in fact, it's almost certainly not going to be constraint feasible here, right? That's one of the really nice things about this, is that it sort of softly penalizes, and it's really good at dealing with infeasible initial guesses. Yeah. Okay. The other comment on this is it works really well for non-convex problems. These are basically like the most forgiving methods for constraint optimization out there. They're super good for infeasible starts, super good for non-convexity. They even work well for like slightly non-smooth problems, stuff like this. They're super robust, which is why we tend to like them. The downside is they're not quite as fast as something like a primal dual interior point method in terms of convergence rate, but they're pretty good. So I think of these as sort of the sweet spot. Okay, so takeaway, fixes ill conditioning.
I have another quick question.
Yep.
Could you scroll up to the updating lambda hat?
Yeah. So here you go.
Yeah, so I'm a little confused how the right-hand side of the equation where it says equals 0 implies that lambda hat should be updated by the minus p c of x term.
So that whole thing's equal to 0. That's just the first order necessary condition. That's the idea here is the fact that lambda tilde minus rho c of x term, that whole term looks like a Lagrange multiplier term, right?
Mm-hmm.
And so therefore, like that whole term, including the penalty, is what my Lagrange multiplier should be. Does that make sense?
Yeah, okay. I guess from a high level, it makes sense. Yes.
So if I start with lambda equals 0 and I only have the penalty, basically the only thing holding me on the constraint is the penalty term, right? And by writing it this way, grouped together, that spot in the KKT conditions is where the Lagrange multiplier shows up normally, right? So what this is telling you is that like minus rho c thing is acting like a Lagrange multiplier. So if I want to estimate my Lagrange multiplier from this thing, the right estimate is that term in the bracket, right?
Yeah. Okay.
That makes sense?
Thank you.
Cool, cool. All right. Anybody else? Yeah.
How does this fix the ill conditioning?
So the way it fixes the ill conditioning is I don't have to keep cranking rho. So maybe I'll write optional. So what this does is lets you converge to the true solution with a finite value of rho because I'm estimating lambda. With pure penalty, there's no lambda. And if I want to get c of x exactly equal to 0, I actually have to crank rho up to infinity. Here, I can leave rho at a fixed finite value, and this outer loop lambda update will converge to the true lambda, at which point I don't need the penalty anymore, right? Does that make sense? There's some subtlety in this. It turns out theoretically, you basically need to hit some threshold rho for that to work on a given problem, and the threshold depends on the specifics of the problem. And it's super hard to calculate what that threshold value is in general. Like it's harder than solving the original optimization problem. So practically what we do is start low and crank it up to some max value that we're happy dealing with, and then stop, and then let the lambda updates take care of the rest. Does that make sense? Cool. All right, anybody else? Cool. All right, here we go. So this converges pretty fast. In particular, it converges super linearly. which is not quite as good as like primal dual interior point methods or whatever, but still pretty good. And it works well for non-convex problems, where the primal dual methods are tricky to use in that context. And in particular, like almost everything we're going to do in here is going to be non-convex, or a lot of it will be, right? For anytime you have a nonlinear system, your trap problems or whatever like this are going to be non-convex. Okay, cool. So now we're going to look at quadratic programs. And these are super, super useful. So these are like kind of currently how MPC is done on most legged robots. They're how most MPC is done on autonomous cars. They're used all over the place. And one of the reasons is you can solve these super fast. You can write solvers for these things that can achieve kilohertz or faster rates. So you can run these really fast online in a loop and sort of get a stabilizing controller out of it. So what this looks like is minimizing a quadratic function, specifically a convex quadratic function. So when I say convex quadratic, can anyone tell me what this function, any caveats to what I just wrote down that make it convex or not? Yeah, so you generally want to, for standard QPs like this, we actually enforce strict positive definiteness for it to be a QP. So that guarantees that it has a unique solution, right? Okay, so we say Q strictly positive definite. And then we're allowed to have linear constraints. So that's what the definition of a QP. So here we'll say AX less than equal to B and C of X equals D. So we're allowed to have a convex quadratic cost function, objective function, and then linear inequalities and linear equalities. And those can be whatever we want, right? Okay, so very useful in control. And can be solved very fast. Okay, so let's go do this. Where is the... Hey, all right. You guys see this okay? No. It's kinda
Yeah.
bad, huh? You guys can, but this is not the best. Is this okay for you guys? I'll try it. Okay, so here we go. So let's see. This is our QP situation with inequalities. Here's a quadratic cost function. I just made this up, right? Pretty straightforward. So here's so this is going to be in 2D. So we've got a two-dimensional quadratic objective, and then we've got a linear inequality with the A's and B's there. And I wrote down the both the C of X and the derivative, the Jacobian matrix, which is just the A in this case because it's linear. So this is this kind of landscape picture that we did before. So level sets of the cost function, and then that line is the linear inequality. And in this picture, the inequality is satisfied when we're sort of up and to the left. So right, the unconstrained minimum would be sort of in the middle of those level sets, but the linear constraint's going to hold us up and to the left. So we can't actually get there, right? Okay, so here's the augmented Lagrangian, like we just wrote down. Yeah. We've got the lambda, we've got the penalty term, all that good stuff. And then here's Newton's method on this guy. It's exactly the same kind of Newton thing we did before. In particular, the Hessian here has the Hessian of the objective plus this penalty term now. What else is there to say about this? Yeah, I don't think there's anything else to say about this. So this is only doing Newton on X, right? As far as this guy's concerned, lambda is a constant that it's passed in, right? Okay, and now we've got some initial guess point. So guessing up here, And the true solution is going to be somewhere around here probably, right? Okay, so the first thing I want to do actually is let's try just doing a pure penalty method and play around with that a little bit. So I'm going to turn off the lambda updates. So we'll keep lambda fixed, and I'm also going to turn off the penalty updates. And let's just see what happens if I run pure penalty. So the first iterate is going to end up, over here. So it's basically, it's going to violate, obviously, but it's sort of in the right spot. If I keep running Newton's iteration on, it's not going to do anything, right? Fixed penalty. If I'm not changing the penalty, it's not changing anything. So it doesn't move. If I now jack the penalty up by like a factor of 10, I'll get a little bit closer. So there, right? I get a little closer. Now, if I jack it up by like another factor, so now a factor of 100, a little bit closer, factor of 1,000, a little bit closer, but I'm never actually going to get there with this method, right? And pretty soon this row is going to get gigantic and I get a conditioning and all that bad stuff. Okay, so now let's look at it with the lambda update. I'll show you a couple of fun things. So maybe we'll just let it rip sort of the full augmented Lagrangian method. So we'll restart ourselves up here. Now we're doing everything. So we're doing this lambda update here, like we wrote down, and we're going to jack up the row like we wrote down. So here we go. That's one iteration, which remember is exactly the same as the penalty method because lambda is 0. Now let's see, second iteration. Now I'm updating lambda and cranking row. Second iteration, I basically nailed it. So, and now if I do like one more of these, not moving, right? So 2, 3 iterations, perfect. So one thing we can do here too, that's kind of fun, is I'll restart this just to show you kind of the whole penalty versus augmented Lagrangian. I'm going to turn off the penalty update. So we do this with just a set fixed penalty and don't crank the penalty. Let's see what happens there. So first round, same as the penalty again. Now remember, with the penalty method, if I leave row fixed, it doesn't do anything, right? Here I'm updating lambda. So it turns out now I keep making progress even with a fixed row, and I'm converged now basically, right? So even without updating row, because of the outer loop lambda updates, I can still converge to the true solution and finite iterations. And this is a particularly easy problem, but holds true in general. Cool. Any questions about this? Yeah.
How do you decide how much the penalty should be cranked up?
Yeah, so you crank it up geometrically, meaning by some multiply by some factor greater than 1. Something between like 2 and 10 is usually reasonable. Usually like 10x is like kind of a standard thing, but it's kind of problem specific hyperparameter tuning game to some extent. But yeah, like don't go too crazy. Something between 2 and 10 is probably the right number. Yeah.
Can we add an additional constraint to the penalty as well? So can the factor be learned using some?
Yeah, you can like adapt it in various ways that depend on how bad the constraint violation is. You can also adapt it on a per constraint basis. So if some constraints are easy and already satisfied, you can leave it alone. If some constraints are being really tough and like hard to sort of crank down, then you crank it up on that constraint. So there's a lot of extensions, a lot of additional tweaks and games you can play to fine tune this, but the basic idea is this, right? And you can play a lot of tuning games for performance. Yeah. Cool. Yeah. Sure. There seems to be one light switch, unfortunately. After the whole room. So I'll like dial it down a little bit. See how that does. Is that better? You do one more notch, but it's all on one switch, as far as I can tell. Okay, so let's sort of go back to notes. Okay, so next up, we're going to talk a bit more. So this was a QP. This is nice convex, right? These are great. What we're now going to talk about is sort of back to sort of the non-convex, nonlinear case, when we'll kind of do some examples of that. But this is specifically because this is the homework. This is homework question 3. So now you have pseudocode for a QP solver. You just have to fix this up for the homework, right? So now we're going to talk about sort of some of these cleanup issues that you have to worry about for like the general non-convex, nonlinear case. Specifically, regularization when there are constraints and line searches when there are constraints, right? So we talked about both these things in sort of the unconstrained case before, and they carry over to the constrained case, obviously, but there's some extra little sort of things to know about when you're doing it in the constrained case. So let's first talk about regularization. And this shows up on question 2 on the homework. So this is, worth knowing about. Okay, so we're going to go back now to sort of the equality case and talk about the primal dual full Newton KKT system situation, right, that we had before. And I should mention also, you can mix and match all these things, right? So you can do augmented Lagrangian on some inequalities. You can do primal dual on the equalities, right? You can kind of use these in various combinations. So let's look at the following problem. Okay, so what we did before, right? Equality. This is going to seem a little weird, but hopefully we're going to get to something that matters and is practical. So on the topic of penalty methods, right? I can replace this equality constraint with some sort of penalty, quadratic penalty, whatever. We're going to invent the sort of theoretical best penalty you could have, but the worst one from a numerical practical perspective. So we might like to turn this into, say, the following thing. Min over x, f of x, plus this sort of exact penalty, which would be the following thing. So we're going to call this p infinity of c of x, where this p infinity thing is 0 when the argument is 0, i.e. when the constraint's satisfied, and then plus infinity otherwise. So does this make sense, everybody? Basically, if I satisfy the constraint, it does nothing, it's 0. If I violate the constraint, it's infinity. So, basically the best penalty you could have in theory, but numerically the worst penalty you could have for doing this in a computer, right? Okay, so we might like this. If we could figure out a way to do this numerically, though, that might be nice, right? Okay, so here's how you get at this numerically in a way that kind of works. So practically, this is terrible. But we can get the same effect by solving this kind of weird nested problem. So min over x of max over lambda f of x plus lambda transpose c of x. So this looks like our Lagrangian, right? And what is going on here? Well, if c of x is not 0, if it's violated, if I take that max over lambda, the value is always infinity, right? Does everyone see that? So for any non-zero c, if I take a max over lambda, I can always blow it up to infinity. And then the outer problem is the one we actually cared about before, right? Does everyone see this? Does it make sense? So this is exactly mathematically equivalent to that infinite penalty. Cool? Okay, so next move is, check that down. Okay, so we can do the same thing for inequalities. That's the next move. So if I have min f of x subject to c of x greater than or equal to 0, I can turn this into min over x. I'll define a sort of f of x. We'll call this one p infinity plus of c of x, and this is defined similarly to before, except it's one-sided now. So p infinity of x equals 0 if x is positive, and then plus infinity if x is violating the constraint, right? So I can turn this into, somebody have some? Did I do something wrong?
No,
Oh, okay. So yeah, here's what this was going to look like, though. In terms of what we did before, it's going to look like almost the same, except we're going to have max over positive lambda. And then we'll, similar to before, we'll have this negative sign here because it actually matters, right? So the idea is, right, if I define lambda to be positive, here, this lambda transpose C term, if C is negative, i.e. violating the constraint, if I take a max over positive lambda now, I can blow that up to infinity, right? And it's gonna give me an infinite penalty. If C is negative, or sorry, if C is positive, satisfies the constraint, then if I take max over lambda, non-zero lambda, then the answer to that's 0 and it drops out, right? Does everyone see this? Does the same thing, right? Cool. And then this term here is our Lagrangian that we know and love, right? Yeah, so if I'm trying to maximize that whole thing, make it as big as possible, if C of X is positive and lambda is positive, the whole term's positive, it's got a negative sign in front of it though. Well, so if that maximization, what's the largest value I can possibly achieve on that term if C is positive and lambda is positive? Well, so like, you're right. I'm trying to make this the maximization problem. I'm trying to blow that thing up as big as possible. The largest value I can achieve on that, if both lambda has to be positive and C is positive, because of the minus sign in front, right? The largest value I can possibly have is 0. Otherwise, it can be negative, right? If it's negative, it's making my cost lower, which is what I want, right? So I want to strictly make it worse by this penalty thing. And the worst I can do is to make it 0 in that maximization problem, right? Does everyone get that? Cool. So it's basically a trick for replacing this infinite penalty thing with an inner maximization, right? Okay. So this is interesting. As just a quick aside, for convex problems, which we'll talk more about convexity later, but you guys are kind of vaguely maybe aware of this. For convex problems, I can switch the order of that max and min, and I can do it either way, which is kind of interesting. Doesn't change the answer. But for non-convex problems, I can't do that. This idea of switching the ordering is called duality. And so has anyone heard of duality and optimization and the dual problem? Yeah. So the dual problem is when I flip those guys. And you'll hear about this in like the theory of convex optimization a lot. Okay, so not true in general though. But the idea is still interesting and useful. Okay, so now the next sort of like where this is going. Okay, so if I look at this, when I do the, like, let's just think about the equality case for now, right? I'm doing this mini max thing, right? When I solve KKT conditions with Newton's method in both X and lambda simultaneously, like we did before, what sort of fixed point am I finding there? In both X and lambda, if I do full Newton on that. Am I finding a minimum? It's a minimum in X, but what is it in lambda? It's a maximum in lambda. So in both X and lambda, that whole joint Newton solve, what kind of point am I finding? Yeah, exactly. It's a saddle in X and lambda. It's a very particular saddle where it's a min in X and a max in lambda. Okay, so that's cool, nice. Okay, cool. So now next question is, when I do Newton on the KKT system, like we wrote down that KKT system where it's got the Hessian block and the two constraint Jacobian blocks, can you say anything about the eigenvalues of that KKT system based on this fact? No, we don't want them to be zero because then it's not invertible. No. So what do eigenvalues mean in terms of like curvature? So we talked about the QP, right? We make, for the QP, we make that Q matrix, the Hessian matrix, strictly positive definite. So positive definite means it curves up, and that means we're getting a minimum, right? So same opposite thing, if I'm getting a maximum, that means it's curving down, it means I have negative eigenvalues, right? Okay, so think now about the KKT system for the Newton method, primal dual thing. So I need dimension of x, positive eigenvalues to have a min over the x variables. And I need dimension lambda, AKA number of constraints, negative eigenvalues to get a max over lambda. Does that make sense to everybody? Cool. So the KKT, we said these have special properties, blah, blah, blah. This is one of the main properties of KKT systems. They need to have dimension x positive eigenvalues and dimension lambda negative eigenvalues. This specifically holds at an optimum, right? Away from an optimum, all bets are off. Although for convex problems, this holds globally. Same kind of deal as before, right? Okay. So this property of is called a quasi-definite linear system. So we talked about positive definite means they're all positive. Negative definite means they're all negative. This is a special flavor. We call this quasi-definite. Okay. All right. So that was a lot of optimization stuff to basically get to the following fact. So I mean, this is good to know about in general. Okay, so we talked about regularizing, right? And in the case where we want to minimize, all the eigenvalues are supposed to be positive. So when I regularize the Hessian in Newton's method, we talked about before, you add some multiple of the identity to try to push all the eigenvalues positive. What do you think we do in this constrained case on a KKT system? Yeah.
+1 and -1.
Yeah, so what we're going to end up doing is regularizing the top left block, the block that's associated with the Hessian of the objective. We're going to regularize that positive. The bottom right block that's associated with the Lagrange multipliers, we're going to regularize that with a minus, with a negative regularizer. So here we go. Okay, so we have
Zach?
something like, yep.
Can you explain what you mean by upper right and lower right block? Like what's
Yeah, I'm writing it
specific
right
feature?
now.
Okay.
So this was our KKT system, kind of deal, x lambda. And then over here, we've got gradient, minus gradient of the Lagrangian, and then minus the constraints, right? And here, this alpha is the regularizer here, right? And this is for some alpha greater than 0. So yeah, top left block, I mean this Hessian block right here. And then bottom right block, I mean this block right here, which is usually all zeros, right? In a KKT system, we talked about before, it's zeros by default. If you need to regularize though, this is kind of the recipe. Okay, any questions about this? You have to do this on question 2 on the homework to get it to work. That's why I'm specifically telling you about this now. This is the only trick you really need to do on that problem. You don't need a line search or anything else. As long as you do this with a reasonable alpha, it'll converge. So homework hints, hooray. Okay, any questions about this? There's a fun bonus question here. When do I have to regularize the lambdas? When do I need that bottom right regularizer? Anyone have any thoughts on that, like a interpretation of that? Why would I need to do that? I'll let you think about that while I switch back to the code. Anyone have any thoughts?
Is that when you're in an infeasible setup and you have to have pulling, and you currently have pulling forces instead of pushing?
So no, but yeah, maybe in the ballpark there. So maybe I'll let you guys chew on this for bonus. Yeah.
None of the constraints are active, so all of.
No, so that would, you just have zeros, right, for lambdas.
Yeah.
So there's a very particular thing that can happen with your constraints. Trivially, actually, it's easy to write this down such that you'll end up needing to do this. If you, I'll leave this as a bonus question. So if anyone's like really wants to wrestle with this, I mean, you could probably Google this and find it, but if anyone can come in and tell me next time, you get like some bonus points on something. Okay. Better yet, come in with a problem where you need it and it doesn't work without it. Okay, cool. So here we're going to try this regularization stuff. We're going to now go to the problem we had last time where it was a quadratic objective and quadratic constraint that we had to be on. So we'll plot this guy again. It's the exact same as last time. So hopefully this looks familiar. So you guys remember this, right? Level sets of the quadratic objective and then this quadratic equality constraint where we need to be on the parabola, right? And here's vanilla Newton like we did before. So this is full Newton. Remember last time we did this, full Newton failed on this guy and Gauss Newton worked. We kind of talked about how you can have weirdo negative eigenvalues in the Hessian because of the constraints and stuff. Okay, so this is kind of digging into that a little more. So here's the constraint. Okay, here's our starting point, right? And we'd like to kind of end up somewhere over here is probably the optimum, right? So we're going to do full Newton on this guy, like we did before. And if you guys remember, we took, so this first step looks pretty good. Take a couple more steps. Seems reasonable, right? But now after like a few steps, we end up, so that's still good. But now this step, we end up like moving backwards, right? And like this thing kind of gets stuck in this weird spot, right? Okay, so let's go look at the eigenvalues of the KKT system. What do we think is going to happen? So this is the whole KKT system, eigenvalues. So what should the eigenvalues look like for this guy? So X is 2-dimensional, constraint is 1-dimensional. KKT system's 3 by 3, 3 eigenvalues. How many positive, how many negative? Let's see what happens. So we got 2 negative, 1 positive. So that's wrong, right? Okay. And remember last time we did the Gauss-Newton thing. So this time we're going to do full Newton, but we're going to regularize to fix this. This is why we didn't talk about the regularization on this guy last time. Okay, so regularize Newton, same deal. It's very similar to what we did last time, but here I'm taking this KKT matrix and I'm going to add positive regularization to the X dimensions, negative regularization to the lambda dimensions. Just as a sort of, I'm going to do this right as long as the eigenvalues are kind of wrong. And this, I should mention also, you should never do it like this in real life. This is like, I'm actually computing the eigenvalues and whatever as I do this. Super expensive, super dumb. In a real, large scale implementation, there's tricks for detecting bad eigenvalues as part of a matrix factorization. So last time we mentioned Cholesky, you'll fail in the middle of the Cholesky and you go back. There's very similar tricks for KKT systems. The standard one's called an LDL factorization, which is closely related to Cholesky, but for indefinite systems, for KKT systems, basically. And same deal with Cholesky, that will fail if there's the wrong eigenspectrum. And you just try it. If it fails, then you go try this trick. Okay, so everyone good on this? We're doing the exact regularization trick we just talked about. Now we're going to start over again and do it with the regularization and see what happens. So here goes. So first step looks basically the same. Here's where we got into trouble last time, right? somewhere around here. So now with the regularization, we should keep trucking. So now we kept going around the bottom. One thing I want to still point out though, so this, I mean, so now it should be clear this is going to work. We'll run it a couple more times. Now it's sort of, there you go. So we got to the answer, right? Cool, converged. So like 5 or 6 iterations. Okay, so regularization, good. Make sure we always go in the right direction. Basically, make sure we don't get stuck in weird spots in like saddles and stuff like that, like we talked about last time. Here's how to do it in the constrained case. The last thing we're going to talk about now is kind of how to fix this behavior down here. So similar to the situation we saw before with just minimization with no constraints, we kind of overshot down here, right? We went pretty far off the constraint manifold, and we would really like to sort of stay closer and track the constraint better. So what we're going to talk about now is how to do line searches when you have constraints. Sound good? Yeah.
Sorry, going back a bit. Should we then not check the eigenvalues on the homework?
Yeah, I mean, you don't need to on the homework. You can for sure for debugging purposes, and that's a small enough problem that you can get away with it. All I'm saying is if you really want to do this for real, if you write a real deal solver, you don't want to do an eigen decomposition like this. It's super naive and like super expensive and super slow. On the homework, it's fine. Yeah, like you can do it for debugging purposes on your homework. You don't need it for the answer. It's like,
so you could just like choose.
yeah, just pick a number. Pick a number as long as it's big enough, it'll work. Does that make sense? Yeah, I mean, if you're debugging to find a big enough alpha, go ahead. Like you can crank it and do an eigen decomposition until you find an alpha big enough for that problem, and then just run it with the fixed alpha, and it's fine. Does that make sense?
Yeah.
Cool. Yeah, I mean, this is bad. Don't do this, you know, whatever. For debugging, it's fine. But like if you're doing this in the loop in a real thing, this is super, super slow and dumb. Okay, cool. So takeaway from that is regularization good, but we still have overshoot issues to deal with. And not bad. Okay, cool. Okay, line search time. So how do we do a line search on a, let's start with what we're going to start off by to like motivate this is how do we do a line search on a generic root finding problem? So when we talked about line searches before, it was specifically in the context of a minimization problem where we did this like Armijo thing, right? The backtracking thing. And to know if we went too far, we just checked the value of the objective. And if it went up or didn't go down as much as we expected, we backtracked, right? So what do we do on a root finding problem? So if I have a root finding problem, I have a big function that I'm just trying to like drive to 0. And the output's a vector, right? Not a scalar. How do I decide if I've gone too far in that context? I don't have a nice objective function that I'm reducing to check. But yeah. Yeah, so this is a super reasonable choice. This, in general, that idea is called a merit function. So you make up some scalar function like the norm of the residual or something like this. That's a scalar that you treat as an objective function and you check to see that that is decreasing. Does that make sense? Okay, so we want to define a merit function. Okay, so basically this situation, right? Find x star such that c of x star equals 0. We want to define a scalar merit function. And we'll call this p of x. That basically measures distance from a solution. Okay, so there's a bunch of standard choices that you can do. So one reasonable one is a quadratic. So you could do something like 1/2 C transpose C equals, 2 norms squared. Another one you can do, which you just suggested, is a norm, and it can be any norm. It turns out will work. So a very popular one is actually the one norm. It turns out, for reasons that will become clear hopefully in a sec. So one norm, but any norm really will work. It literally just has to be some scalar function that tells you how far you are from the solution, right? Okay, so now that we have this merit function, we just do Armijo like before on the merit function. So last time, we had the objective that just acted like a merit function automatically for us. Now we have to make one up, but now we just do Armijo again.
Hey, Zach.
Yep.
Quick question. What's that value next to the 2 norm?
This is 2 norms squared. Sorry, this is just saying these are the same thing.
I meant on the left side. Is that a 1/2?
Oh, so that's not a 2 norm, right? That's a quadratic, and that's a 1/2. Yeah,
Okay.
and that's just by convention because it makes the gradient nicer.
I see.
Because the factor of 2 drops out when you take the gradient, right? Okay, so now we do Armijo on this guy. What that looks like, right? Just like before, we have this backtracking alpha thing, and we do sort of while P of x plus delta x, which is our Newton step, is greater than the old value of P plus a first order Taylor approximation of what we think the decrease should be with these sort of tolerances on it, right? So here's the gradient of P. And this guy is the step size. And then this guy is our tolerance, right? Just like last time. What the hell? Come on. Sorry for stupid technology. Why do you have to suck so much? What the? Sorry, guys. Let's try this again. I've had the worst luck this time. Literally, the other week, my laptop completely died and bricked itself in the middle of Zoom lecture. Like, I don't know what is going on with all of my electronic doodads this time. Now this thing's refusing to connect to my Mac. Like, what the hell? Come on. Okay, is it working now? It did something. Hey, it's back. I hate all of this. Okay, excellent. We're back. Sorry, guys. Okay, cool. So, like last time, Armijo, this whole term over here, right? This guy is just the first order Taylor expansion of the merit function, and it's saying, we expect this must decrease according to the first order Taylor expansion, and then I want it to actually do that, up to some tolerance. So if it's not within some tolerance of the first order Taylor expansion, then I'm going to backtrack. So I'm going to do alpha gets C times alpha until that condition holds, and then I'm going to do my update. And C is some factor less than 1, right? So cool. That's the same as last time, right? Armijo. Now we just do it on this merit function guy instead of the objective function. Okay, so should be kind of obvious. Now we're going to say, how do we do this for constrained optimization? And constrained optimization is kind of a special case of root finding, right? We're doing root finding on the KKT conditions. So we can basically do these same tricks. But it turns out there's some new ones you can do for constrained optimization. Okay, so we're now doing, say, min over x, f of x, subject to, we'll do both inequalities and equalities here. So we're now going to sort of write down the Lagrangian for this guy, just mostly for notation purposes. So we're going to have f of x, and then we're going to have a Lagrange multiplier for the inequalities is going to be lambda. And then our Lagrange multiplier for the equalities is going to be mu. This is just bookkeeping. There's nothing special about any of this. And remember, the negative sign matters on the inequalities. For the equalities, it doesn't matter, plus or minus, whatever. Okay, so now there's lots of options. Okay, so here's some options. We can do the same stuff we just said for root finding, where we can do it on the KKT residual. So we can just treat it like a root finding problem on the KKT conditions, and we can do something like that. This guy, right? Which, to be super specific, what we need here is the following thing. So this would be sort of gradient of the Lagrangian with respect to x. And then the inequality violations. And then the equality violations. So that's what that is. So this is fine. We can do this. There's actually, seems obvious based on what we just said about root finding. Turns out this is basically never used in practice for a very specific reason that might not be obvious, but we will make it obvious in a second when we go to the code. Okay, so that's what we would do naively based on the previous conversation. Another one we can do is objective plus some norm on the constraint violations. So this is pretty intuitive also, right? And again, the most common norm is the one norm for these things, but any norm works. And we've got some hyperparameter row up here to like trade off how much we care about constraint violation versus how much we care about minimizing the objective. And again, this you have to tune this. And any norm works. So it turns out this is one of the most common ones. Then there's one more that's super common that is very related to something we talked about earlier today, which is the augmented Lagrangian. So it turns out augmented Lagrangians make great merit functions. So if you're doing an augmented Lagrangian solver, it comes with a merit function for free, basically, which is also another nice thing about augmented Lagrangian methods. But people also use the augmented Lagrangian as a merit function in other solver techniques as well. So fun fact. And these two are the common ones. So this one up here, which has like just a norm penalty on the constraints, is super common, and the augmented Lagrangian is super common. And so this looks like, f of x, Lagrange multiplier, Dealey, for both sets of constraints, and then violation sort of penalties for both sets of constraints. Okay. Questions about this? I don't know. Menu of options. We'll do it now and check it out a little bit. Okay, so merit functions. Let's go look at some merit functions. Okay, so what we're going to do is same problem as before. So quadratic objective, quadratic equality constraints. Same picture as last time. We're going to do Gauss-Newton just because. And we're going to start specifically at this point here where you get really bad overshoot. So we'll do a vanilla step without a line search. And so you just go super overshoot way far from the constraint, not what we want, right? So let's go fix this with a line search. So the first one we'll try is the KKT residual. So here it is, right? This is a gradient of the Lagrangian and constraint stacked. So those are our KKT conditions that we're trying to drive to 0. And that's KKT residual. And we're just going to take like that thing squared or whatever, right? Okay, so let's turn this on and start doing line searchy things. And let me reset this guy. So now we'll do Newton with line search and see what happens. So notice we took a much shorter step now, didn't overshoot so much. And next, we stay much closer to the constraint, and we end up, getting the answer quicker in the end, fewer iterations. Okay, so question now is why don't I like this one? Why don't I like the KKT residual flavored lines, merit functions? So let's go look at it real quick. So this seems fine. I'm already computing this guy. But remember, to do our MIHO, I need the first order Taylor expansion of the merit function to compute that expected decrease. Look at the first derivative of this merit function. It's basically as expensive to compute as the Newton step was. So it's super expensive to compute that gradient of the merit function in this case, because it's the full KKT system, basically. So to do the Armijo thing, super expensive. So I don't like it for that reason. This one's super expensive. So any of the ones that basically merit functions that look at KKT residual, the gradients are really expensive. We don't like that. Okay, so let's go do one of the other ones now. So here's, yeah.
You're saying because we were doing Gauss-Newton here, so we weren't, prior to doing this, we weren't taking that second derivative?
Yeah,
If you were
so
doing full Newton and you already had that second derivative available, would it be more effective?
so maybe. So essentially, like, this works perfectly reasonably if you have a cheap way of computing that gradient. And that's basically why the other ones are popular. If you, in your particular problem, your particular setup, you have a cheap method for computing that gradient, cool, go ahead. Yeah, okay, so the reason these ones are popular, so here's the other one, right? So this is objective plus one norm of the constraint violation. And we're going to set rho to 1 for now. So here, note the gradient of this guy's dirt cheap. It's like just sine of the constraints or whatever. So this gradient's easy to write down, super cheap to compute. That's why this is popular, basically. So let's switch it out for this guy and reset up here and run this one a few times and see what happens. So it's very similar behavior. We kind of track the constraint pretty closely and land on the answer. This looks almost exactly the same as the last one, right? But generally, this will be cheaper. Let's check something out, though. Okay, so this row up here, it's a sort of a tuning parameter, right? That you sort of tell how much you care about minimizing the objective versus how much you care about satisfying the constraint. Let's sort of jack that up to 10. So it says I really care about the constraint violation a lot, and let's see what happens when I do that. So reset again. Let's run this guy again. So check this out. It's taking super tiny steps now, basically backtracking a ton so that it doesn't leave the constraint manifold. This is because, right, the constraint's curving and the step is computed based on a linearization. So in these kind of situations, you end up like backtracking a ton and not making a lot of progress. So you have to be really careful in tuning that row with some of these guys to make sure you don't suffer from this sort of uber slow convergence, super tiny steps situation. This actually has a name. Does anyone know what this is called? None of my students, yeah.
I have a slightly different question.
Sure.
If you jack up row, you also increase the tolerance to compensate.
You can, yeah, you can play games with, but this is a specific problem that you will end up with sort of regardless of tuning on sufficiently nonlinear constraints. Basically, if the constraint's super curvy, this is always going to be a problem because Newton's relying on a linearized constraint. So this specific problem of like super slow convergence when you have large constraint curvature actually has a name. It's called the Maratos effect. I don't know, fun fact. It shows up in nonlinear optimization, and it specifically has to do with backtracking line searches where you have like this sort of situation where you make super slow progress. And there's tricks for dealing with it that we won't necessarily get into. Okay, so important to tune rho properly for your problem so that it doesn't sort of bog you down too much. Now let's look at the augmented Lagrangian. So standard augmented Lagrangian deal, like we've talked about a bunch. Rho equals 1. Reset this guy. Let's go run it. So 1 took a bigger first step and then like sort of nails it in like 2 iterations, which is, I mean, I've been hyping up augmented Lagrangian methods a lot. This is not necessarily representative of anything. It just so happened with the rho value and tuning parameters on this particular problem, this worked the best. Probably not true in general, I don't know. The takeaway message though is that basically this one with the one norm constraint penalty and the augmented Lagrangian here, these two guys, they're both relatively cheap to compute the gradients of for the Armijo rule and are both like the standard popular choices. So like all the large scale kind of off the shelf solvers will do pretty much one of those 2 options. Cool. Okay, any questions about this? Line searches, cool. Constraints, yeah.
So the augmented Lagrangian method can still have like the slow convergence problem.
Yeah, absolutely. Yep. So for very non-linear, it specifically has to do with this fact that it's kind of intuitive geometrically. If you have a nonlinear constraint, that means the constraint surface is curved, right? Versus a linear constraint, which is a straight line. When you do the Newton step, you're linearizing the constraint inside there. So the Newton step is computed based on a linear, effectively tangent plane or hyperplane to the curved constraint. So if you take a big step along that linearized constraint, you're always stepping off the curved constraint surface. And so if you have a big sort of constraint penalty in your line search, you're going to backtrack like crazy because the bigger step you take on this tangent thing, if your constraint's curved, the bigger step here, the farther you are off the constraint. So like the only thing you can do in a backtracking line search in that situation is backtrack a ton to get closer to the constraint, right? And so this is like a classic sort of like classic issue with nonlinear constraint optimization that is famous enough that it has a name, and there's a bunch of tricks for trying to deal with it. Okay, cool. Everybody good here? So let's see, what are we, did I have anything else nice to say here? I think this is just, yeah, I don't think this was anything interesting. Okay, cool. I think that's it for that. So to sum up, my pad is still working, hooray. Okay, so P of X based on KKT residual is often expensive to compute. So not super common in practice. Excessively large penalties on these on the constraints. Can cause problems, i.e. will lead to super slow convergence because you'll backtrack a ton and to stay super close to the constraint manifold and then just not make any progress. So we don't like that. And in particular, the ways to fix that are fancier line searches in a lot of cases and extra tricks in your Newton solve. And then finally, these augmented Lagrangian methods sort of come with a merit function for free, right? we can use the augmented Lagrangian as a merit function. So that's kind of nice. Okay, we have 4 minutes left. This is the end of our discussion on optimization, sort of generic numerical optimization topics. This should cover everything you need on the first homework. The next thing to talk about is trajectory optimization slash optimal deterministic optimal control, we'll call it to be fancy, but that's what we're going to talk about next. I think it's probably a good place to stop instead of biting off a whole new topic with 3 minutes to go.